Okay. So, let us start the new week, which is and this week we will discuss about the speech features extraction. So, all kind of that you can say that speech production systems we know. Now, this week we try to find out what kind of speech features or why it is required the features. Okay. So, extraction of speech features, this week title I can say the extraction of speech features. If you see any speech signal, I will show you in full edit softwares. If you say this is a speech signals, if I want to see the whole sentence, this is a whole sentence of the speech signals. Okay. So, there if you see along the timeline there is a different speech event. If you say that this is a speech event, this is maybe another speech event. So, I can say along the timeline speech is different or characteristics of the speech signal is different. You may say digital speech itself is a feature. Yes, once I do the sampling, each sample can have a features, acts as a features. So, suppose we said that okay, speech sample can be a features. Now, if you see, if I consider a speech segment of 1 second, how many samples will be there? If it is recorded with 16 kilohertz, then I can say 16 kilo sample will be there. Even if I make a window, let us 20 millisecond window. So, 320 sample will be there, 320 sample. If I compare sample by sample, then the feature factor dimension is 320. Other way is that if I say this time after one day or after next time two signals are sound like but if I recorded those two signals and I try to compare, I found they are different. Sample wise they are different. So, if I take the sampling as a feature extraction, it is not that good. So, what will be the speech features or why it is required? So, if I say that, then I can start from here. What is features or parameters, whatever I said. So, what is speech features? I can say let us take the speech signal and find out some parameters which is in lower dimension, or I can say that there is a speech signal. I take a signal segment and I represented in such dimension which represent the speech signal itself. So, I can say the features is a measure of property of the speech signal. So, I can say some property of the speech signal will be there, that may be a natural and non-natural, and those property actually represent the speech signal. So, reason for feature extraction, redundancy. If I say if I compare sample by sample, there may be many samples which does not require to represent the signal. So, I can say like that. Suppose if you say to extract some features by which you can remember me. So, actually you are not remembering my each and every. So, suppose I show you my image, you are not remembering each and every pixel of my body. So, you are finding out some features which represent my body, but they are not exactly my body. So, what I can say that redundant information which is exist in my face, you can discard those and find out the salient point which actually represent my face. So, features extraction or the speech features in feature domain is nothing but a reduce the redundant information, or you can also remove the redundant information. If there is a 320 dimensional vectors, any classifier or any kind of comparison when I do, it is computationally complex. Every member I have to compare. So, there is a 320 member, even if simply equidistant distance. So, dimension is increased, computational complexity is very large, and also modeling. Suppose I want to model that using those features. So, if the features dimension is very high, the modeling is very difficult. So, actually feature extraction means that I want to convert this speech segment in a such a way, or such a, I can say that I can represent this speech segment with a such a vector which actually represent these signals, and it in redundance, or that means all redundant information is deleted and only key informations are there to form a vector which the vector represent that speech event. So, that is called speech features. Okay. So, there are many kinds of speech features. Some things may be natural speech features, something may be unnatural speech features. If it natural speech features, if I say, if you see in the speech waveform here, there, if you know that acoustics, phonetics. So, if you see natural speech features are the phoneme, different time consist of different phoneme. So, that can be a natural speech features. If you see the movement of the F0, fundamental frequency during the whole sentence is not a constant. So, movement of the F0 itself can be a features, phoneme can be a features. If you see the duration, if I say this is the duration of the saw, this is the duration of the consonant to vowel transition, this is the transition vowel duration, this is the vowel to consonant transition. So, all duration kinds of speech can be a features. Then I can say articulation, place of articulation in a speech event has a features. Ka, velar consonant, pa, bilabial consonant. So, that can be a speech features. So, some features are natural, some features are non-natural, they are abstract represent of the speech event, but some features has a meaning, phoneme, articulation, duration, all has a real meaning in the speech waveform. Okay. Similarly, form and frequency, if you remember, we plot the F1, F2 plot of all vowels. So, form and plot of the all vowels. So, using the F1, F2, F3, all formant representation can be a features by which I can identify the speech signal, or by, on the other hand I can say those formant frequencies represent the speech signal. Okay. So, formant may be a natural features. So, there is some non-natural features that not natural, like the spectrum, linear predictive coefficient, they are represent the speech signal, but literally they does not have a meaning. So, if I say the LPC coefficient A1, A2 up to AP all represent that speech frame, there is the parameters or features, but they are non-natural features. Similarly, spectrum, then the MFCC, vocal tract area functions, all kinds of features are there which is non-natural. So, we discuss about the extraction of some natural features and non-natural features. Now, the problem with feature extraction is that whatever the features is there, the extraction procedure must be robust. That means, what is robust? That means, if this is the speech signal, if I this time I extract the features, if the next time also I extract the features, I will get the same features for the same speech signal, and they should exactly represent the segment. So, sometimes this features is very high, and if I extract in next time this features is very high, then there is some problem. So, the main problem is that we should call those are the speech features whose extraction procedure is robust and also computationally less complex. If it is computationally very complex, then the feature extraction may require much more time. So, I cannot develop the systems which is real time. Okay. Any kind of application, if you say speech recognition, speech synthesis, speaker identification, LPC coefficient, LPC coding or any speech coding, all are nothing but a extract the speech features, and using those features I can apply any kind of classification, or I can coding, or I can synthesis algorithm, so that I can revert back the signal. So, what I can say, the speech features actually the representation of the original speech signal. Using those features I can develop different technology which can be say as a speech application. Okay. So, during this whole week we discuss about the those features extraction. Okay. Now, I come to that. If you see in the slides, or if you see along this speech signal, if you see the spectrogram is different in different segment, or I can show you in here. If you see the speech segments properties or signal property of the speech segments are different in along the time. If I say this time this portion is completely silent, this time vocalic, this time noisy, vocalic, noisy, silence, burst. So, all kinds of speech events are there, and if I say the signal space different time, the speech segment signals are different. So, if I extract the features for this small segment, then I can say those are called segmental features. Have you understand or not? If I extract the features for the segment, then I call segmental features. There may be some features which vary across the segment, like that F0 movement, duration of the speech event. So, they are vary across the segment. So, I can say those are called supra-segmental features. So, I can say during the based on the extraction, I can say two types of features. One is called segmental features, another is called supra-segmental features. So, segmental features which related to particular segment, maybe a consonant to vowel transition is a segmental features. Pure occlusion period is a segmental features. Burst is a segmental information. So, if the features is extracted segment by segment or for a particular segment of the speech signal, then I call this is a segmental speech features. If the features is extracted across the segment, then I call it is a supra-segmental speech features. So, if I say segmental speech features, all the speech event, phoneme, maybe part of a phoneme also segmental speech features, occlusion period, burst, consonant to vowel transition. So, all are segmental features. If it is supra-segmental features, movement of the fundamental frequency, change of duration of phonemes or syllable, and if you say the duration profile, amplitude profile, change of amplitude across the whole speech is also a supra-segmental features. Okay. So, speech features are basically two types, one is called segmental features, another is called supra-segmental features. So, F0, duration, amplitude profile are the supra-segmental features. Segmental features I can say phoneme or part of a phoneme is also a segmental features, like occlusion period, burst. If I am able to extract the burst, occlusion period, BOT, all are segmental information. Okay. Now, how do we extract the, I will come supra-segmental features, I will come later on, that intonation, pause, duration, trace, all are called supra-segmental features, how they extract. So, we will discuss about the two kinds of methodology, one is segmental features extraction, another is supra-segmental features extraction, and supra-segmental features are used to model speech prosody. Now, concentrate on segmental features. Okay. If you see, if I choose a segment of the speech signal, let us I choose this segment, and if I analyze the frequency, see this is the frequency spectrum of that segment. So, in frequency domain, the speech is represented in a frequency domain of this segment. Now, if you see, there is a movement of the formant. If I choose small segment, there is a movement of the formant. So, you can say the peak denotes the frequency component of the signals. So, if you see these slides, there is this is the spectrum information, and if you see if the red line is the envelope of the spectrum, and those peak of the envelope denotes the formant. So, if I say formant is my features, so I have to extract those formant. How do I find out those formant? So, I have to find out an algorithm by which I can robustly extract the formant frequency. Okay. So, that is it. I require an algorithm by which I can extract all the formant frequency F1, F2, F3, F4. One of the methods is that you know that if there is a LPC coefficient A1 to AP, if I take the frequency transform of those LPC coefficient, they are actually represent the formant position of the signal. So, formant frequency are extracted using the LPC LPC spectrum analysis also. So, I want an algorithm by which I can extract the formant frequency, then it is called formant frequency extraction, and those formant frequency for a particular speech segment. Okay. Now, if you see in parameter domain, there is a lot of speech parameters or features. One is called filter bank. So, features parameter extraction methods, lot of like LPC we have discussed, LPC parameter extraction method we have discussed. So, there is a frequency domain parameters, there may be a time domain parameters. So, features can be extracted from the time domain representation of the speech signal. So, if the speech signal is this, so from the time domain representation I can extract the features, then I call time domain features. From the frequency domain representation, from this representation if I extract the features, then I call frequency domain parameters. So, based on this analysis, we can say there is 3 types of parameter, frequency domain parameter extraction or 3 types of parameter extraction methods. One is called frequency domain parameter extraction methods, time domain parameter extraction method, time frequency both parameter extraction methods, and extracted parameter are called parameters. So, if the LPC parameter extraction extracted using LPC analysis, then all coefficient A1, A2, A3 all are called LPC parameters. So, those represent the speech signal for a particular speech segment. Okay. So, if the features is extracted segment wise, so it is if all features are extracted segment wise, that I will come later on why it is. Then there is a called frequency domain parameter, filter bank analysis, short term spectrum analysis, spectral analysis, formant parameters, MFCC, delta MFCC, all kinds of parameters are called frequency parameter. Time domain parameter, LPC, shape parameter. Frequency time domain parameter, perceptual linear prediction and wavelet analysis. Okay. So, all parameter extraction methodology, we try to explain one by one. So, you learn how to extract the all kinds of speech parameters. Okay. Now, if I say this is the whole speech signal, I say the parameters are extracted segment wise. Now, if I say the phoneme or I say phoneme is a segment, how do I define the phoneme boundary in a continuous speech? Manually I can listen and I can find okay, up to here it is a sha kind of signal. But think about, I want the extraction method by which automatically I want to extract what kind of phoneme it is. So, instead of that is very difficult. So, instead of extracting that what kind of phoneme it is, I want some kind of representation of the signal which is unique in certain domain. So, I can say probably if this is this kind of parameter extraction and those parameters belongs to particular phoneme may be so or may be palatal so. So, although the extraction of phoneme or part of a phoneme is a meaningful features or natural features of the speech signal, but detecting the boundary of a phoneme is very difficult in continuous speech. So, how do I can find out a phoneme po? How do I can find out phoneme pho, or how do I find out phoneme so? So, instead of finding out phoneme so, let us blindly analyze the speech signal frame by frame and assign each frame to a particular phoneme, or I can say the extracted parameter represent this frame. Later on, I try to classify whether this frame belongs to so or po or pho. So, that is my job. So, I can say the features are extracted segment wise and they are the representation of that segment. Either it can be time domain or it can be frequency domain. So, if those features are extracted frequency representation of that segment, then I call frequency domain parameter. If they are extracted from the time domain representation of the signal, then I call it is a time domain parameter. Okay? Okay? So, pitch features, natural features like phoneme, we are not extracted really. So, what we are doing? We try to design an algorithm by which segment, or you can say the framing. I done the framing of the speech signal, frame by frame speech signal will be analyzed and either time domain or frequency domain parameter will be extracted, which will represent exactly that frame of the speech signal. Okay. So, that is my job. Suppose I have a speech. So, first discuss about the filter bank analysis. What is filter bank analysis? Okay. Come here. So, we will discuss about the filter bank analysis. So, suppose forget about the slides, let us SN is my signal, speech signal, recorded speech signal. Okay. So, let us I give a real example. I recorded my name and my name has consist of the signals of let us 1.5 second and that signal is recorded 16 kilohertz. So, I can say in 1 second there is a, I can say there is a 1 second 16k sample is there. So, 1.5 second or I can say 1.5 second. So, there will be a 16 plus 8 is equal to 24k sample and k sample. If you see, if I recorded my name, so different speech event has different kind of speech signal. So, I am not analyzing whole speech signal at a time and represent by a single vector. So, instead of doing that, if I do that, then time resolution I completely lost, as we discussed in the frequency analysis. So, what I will do, instead of analyzing that, I will hold that this is my whole signal and I frame the signal. So, I can say I window the signal. So, I can say let us take 20 millisecond window and shifted the window by 10 millisecond. So, I can say in a 1 second I will get 100 frame, 100 such frame, 10 millisecond, 10 millisecond, 10 millisecond. So, 100 such frame and each frame, from each frame I get a representative feature vector. Okay? That is my job. So, in 1 second or again 1.5 second I can get at least 150 frame and each frame is represented by a some feature vector. Okay? Those features are those features are extracted using filter bank analysis. So, what is filter bank analysis? If I say, so whole speech signal, let us SN is there. Okay? this is my SNN, which is the nth frame of the speech signal. This should be passed through some parallel filter. I can pass that signal with a parallel filter, some parallel filter, and each filter has a pass band. So, this is 0 to 100 Hertz. This is again I said 100 Hertz. So, there is a non-overlapping filter. There may be non-overlapping 100 Hertz to 200 Hertz. Then 200 Hertz to 300 Hertz. So, each filter has a particular pass band. So, from each pass band I will get the power if that particular frequency component is there in the speech signal. So, if there is any component 0 to 100 Hertz, so output of the filter is nothing but a 0 to 100 Hertz representation of the signal. Okay? That is 100 Hertz to 200 Hertz signal, that is 200 Hertz to 300 Hertz signal. So, now if I quantize the power, whatever the frequency component is there, sum their power and take as a parameter A1. So, I can take those sum as a parameter of A2, those sum A3. There is a m number of filters. So, I can say up to am. So, this A1, A2, A3 and am represent the feature vector which is extracted using the filter bank analysis. Okay. Am I clear? Now, how to design those? So, those filters are particularly nothing but a band pass filter, because there particular band is passed. If the whole signal passes through this filter, so 0 to 100 Hertz band will be passed. And once collected the pass band signal, I find out the sum energy of 0 to 100 Hertz signal. Okay. So, I can say 0 to 100 Hertz signal, whatever the energy is there, I can sum them, or I can take the average energy of the 0 to 100 Hertz. So, that energy represents one parameter. So, am parameter, m number of parameters are there, which is designed by a filter bank analysis. Is clear? Now, those filters, those design of those filter has a different methodology. So, I can design them either overlapping, I can design them non-overlapping, quadrature mirror filter, lot kind of design of those filter can be done. And whatever I design, the output is called filter bank analysis of the speech signal. So, each of the filter output, this is the complete filter bank analysis model. If you see, the filter passed through a band pass filter. So, this is the first band, second band, third band, up to q number of band is there. So, if I say I have a signal called, I have a 16 kilohertz sampling frequency. So, what is the baseband frequency? Baseband frequency signal is 8 kilohertz. So, my speech signal has a component up to 8 kilohertz. So, if I say I want to design 100 hertz band filter. So, how many filter will be there? Every filter is 100 hertz, non-overlapping condition. So, I can say 8K divided by 100 hertz. So, I can say it is nothing but a 8000 divided by 100 hertz. So, I can say there is a 80 filter will be there. So, Q is equal to 80. So, 80 band pass filter will be there, and each output filter, then there is non-linearity, I can pass through a non-linearity, and then low pass filter, and then sampling rate reduction, and then amplitude compression, and I get a parameter x1m. Okay. So, that each filter output I can define each filter output if the signal is, so there is a filter output will be 0 to n number of, if the signal content each frame has 0 to n number of sample, each filter output will be 0 to n number of sample. Okay. So, that output I can quantize, or I can find out the average energy. So, that is my parameters. Okay. So, this is the complete filter bank analysis. Now, how to design those filter? I can uniform filter bank design. I can say every filter is 100 hertz and there is a no overlapping region. I can say every filter bandwidth will be determined by a log frequency scale, or I can say every filter bandwidth will be determined by a male scale, which is the perceived frequency by a human being, which is the scale of perceive of human being frequency. So, how the human being perceive frequency in male scale? So, I can design those filter bandwidth in a male scale, or I can say those are the overlapping filter. So, I can say the filters are designed using 50% overlap. So, if this is my first band 0 to 100 hertz, next filter will be 50 hertz to 150 hertz. Okay. So, then I can say they are 50% overlap filter bank. Okay. Then I can say the bandwidth of the filter is not linear. So, not always 100 hertz. In the low frequency, they may vary every year 100 hertz, but the high frequency bandwidth may be larger, and that bandwidth may be determined by male frequency, male scale. So, all kind of things we can use and we can design the filter and find out the filter bank parameters. So, like this uniform filter bank, then I can go for the nonlinear log frequency filter bank, then I go for the male scale filter bank, and structure of the filter also not, I do not want this to be flat, I can want there will be triangular filter or rectangle. Instead of rectangular filter, I can say there are a triangular filter. I find out the energy within that triangle. Okay. So, whatever I design here, this is called filter bank analysis. Okay. So, now stop here. So, next lecture we will go for the another methods for parameter extraction. Okay. Thank you.